You're holding your phone right now, or maybe you're sitting in a chair. The screen in front of you feels solid, the air around you feels empty, and somewhere in your mind you've accepted that the world operates on rules, predictable, consistent, the kind that let engineers build bridges and physicists calculate orbits down to the millimetre. But there's a problem, a quiet, persistent problem that's been sitting at the foundation of modern physics for nearly a century. When scientists look closely enough at the fabric of reality, at the behaviour of light, electrons, atoms, the rules stop making sense. Not in a vague philosophical way, in a precise, mathematical, experimentally verified way. And the strange part isn't just that these paradoxes exist, it's that they refuse to go away. In 1935, Erwin Schrödinger proposed a thought experiment. Not as a celebration of quantum mechanics, but as a critique. He imagined a cat sealed in a box with a flask of poison, a radioactive atom, and a detector. If the atom decays, the detector triggers, the flask shatters, and the cat dies. If it doesn't decay, the cat lives. According to quantum mechanics, until someone opens the box, the atom exists in a superposition, both decayed and not decayed at once, which means, following the logic strictly, the cat is simultaneously alive and dead. Schrödinger didn't propose this to show how clever quantum theory was. He proposed it to show how absurd it becomes when you try to apply it to everyday objects. He wanted to force physicists to confront the uncomfortable gap between what the math predicts and what actually happens in the world. But instead of resolving the paradox, the scientific community absorbed it. They gave it a name. They taught it in textbooks. And nearly 90 years later, we still don't have a clean answer for why a cat can't be both alive and dead, even though the equations say it should be. The measurement problem sits at the heart of this. In quantum mechanics, particles don't have definite properties until you measure them. Before measurement, an electron doesn't have a specific location or momentum. It exists as a wave function, a mathematical description of all possible states it could be in, weighted by probability. The wave function evolves smoothly, deterministically, according to the Schrödinger equation. But the moment you measure the electron, something changes. The wave function collapses. The electron suddenly has a definite position. The measurement forces it to choose. And that's where the trouble starts. The Schrödinger equation doesn't describe this collapse. There's no mechanism in the math that explains when or how it happens. It just does. Measurement does something to the system, but quantum theory offers no account of what that something is. It's as if the universe has two sets of rules, one for when you're not looking, and another for when you are, and no one can explain why. Different interpretations try to patch this. The Copenhagen interpretation, the oldest and most widely taught, treats measurement as a fundamental event that collapses the wave function. But it doesn't explain what counts as a measurement. Does it require a conscious observer, a laboratory instrument, a stray photon bouncing off the particle? The theory doesn't say. The many worlds interpretation avoids collapse entirely by claiming that every possible outcome actually happens. The universe splits into parallel branches, and you simply find yourself in one of them. In another branch, the cat is dead. In this one, it's alive. Both are real. You just can't access the other branches. It's a logically consistent picture, but it comes at a staggering cost, an infinity of unobservable universes multiplying with every quantum event. Other models propose objective collapse mechanisms, new physics that modifies quantum mechanics at certain scales or under certain conditions, but none of these mechanisms have been observed. And so the question remains open, not because physicists haven't thought about it, but because every answer introduces new problems. What makes this especially uncomfortable is that quantum mechanics works. It's not a speculative theory. It's the most successful framework in the history of science. The predictions it makes about atomic spectra, chemical bonds, semiconductors, lasers, all of these match experimental results to absurd levels of precision. Engineers use quantum mechanics to design computer chips. Doctors use it in MRI machines. The device you're reading this on wouldn't function without it. And yet, when you ask what the theory actually says about reality, what it means for a particle to be in superposition, or what happens during measurement, you find that physicists don't agree. They agree on how to use the equations. They agree on what the equations predict, but they don't agree on what the equations are describing. Some say the wave function represents objective reality. Others say it's just a tool for calculating probabilities with no physical substance. Still others say the question itself is meaningless. And this isn't a historical quirk from the early days of quantum theory. It's still the case now. The interpretation problem hasn't been solved, it's been deferred. Richard Feynman, one of the architects of quantum electrodynamics, said it plainly. I think I can safely say that nobody understands quantum mechanics. He wasn't being modest, he was acknowledging that the theory gives you a recipe for making predictions, but it doesn't give you a coherent picture of what's actually happening. You can follow the recipe, you can get the right answers, but if you try to visualize the process, if you try to construct a mental model of what an electron is doing before you measure it, you end up in contradiction. And that's not a failure of imagination. It's a failure of the theory to provide a consistent ontology. We have the math, we don't have the story. The double-slit experiment makes this painfully clear. Fire a single photon at a barrier with two slits. On the other side, place a detector screen. If you don't measure which slit the photon passes through, it behaves like a wave. It goes through both slits at once and interferes with itself, creating a pattern of bright and dark bands on the screen. But if you place a detector at the slits to see which one the photon uses, the interference pattern disappears. The photon suddenly behaves like a particle. It goes through one slit or the other, not both. The act of measurement changes the outcome. Not because the measurement disturbs the photon in some clumsy mechanical way, but because the question you ask determines the kind of answer the universe gives you. Ask which slit, and you get a particle. Don't ask and you get a wave. The photon doesn't have an independent reality that exists regardless of how you look at it. Its behavior depends on the experimental setup. And this isn't a quirk of photons. It's been demonstrated with electrons, atoms, and even large molecules. The wave-particle duality isn't a property of small things. It's a property of the measurement process itself. This raises a deeply unsettling possibility. Maybe the universe doesn't have definite properties until something forces it to. Maybe reality is fundamentally relational. It only crystallizes in response to interactions. The photon doesn't decide to be a wave or a particle. The system as a whole, including the measurement apparatus, defines what kind of question is being asked, and the universe answers accordingly. If that's true, then the idea of an objective, observer-independent reality, the idea that things exist in definite states whether or not anyone is looking, might not hold. And that's not a mystical claim. It's a straightforward consequence of taking the math seriously. Einstein hated this. In 1935, the same year Schrödinger proposed his cat, Einstein co-authored a paper with Boris Podolsky and Nathan Rosen arguing that quantum mechanics must be incomplete. The EPR paradox, as it's now known, focused on entanglement. If you create two particles in such a way that their properties are correlated, say, their spins are opposite, and then separate them by a large distance, quantum mechanics predicts that measuring one particle instantly determines the state of the other. No matter how far apart they are, Einstein called this spooky action at a distance and argued it couldn't be real. He believed there must be hidden variables, properties the particles carry with them, that determine the outcome of measurements in advance. Quantum mechanics, in his view, was just an incomplete description of a deeper, deterministic reality. But in 1964, physicist John Bell derived a mathematical test. He showed that if hidden variables exist and if the universe obeys locality, the principle that objects are only influenced by their immediate surroundings, then certain statistical correlations between measurements must satisfy an inequality. Quantum mechanics predicts violations of this inequality, and experiments performed over and over since the 1970s have consistently confirmed the violations. The universe, he doesn't obey Bell's inequality, which means either hidden variables don't exist or locality is wrong, or both. Einstein's intuition, elegant as it was, doesn't match reality. And here's where things become even stranger. The quantum Zeno effect. If you measure a quantum system repeatedly, you can actually prevent it from evolving. Normally, an unstable particle will decay over time, but if you keep checking whether it has decayed, the act of measurement resets the system. The particle stays in its initial state. It's as if watching the system freezes it in place. The effect was first proposed theoretically, then demonstrated experimentally in 1990 with trapped ions. It's now used in commercial magnetometers. The principle is simple. Continuous observation prevents change. In classical physics, this would be absurd. Watching a ball roll down a hill doesn't stop it. But in quantum mechanics, observation is not passive. It's an interaction that collapses the wave function. And if you collapse it frequently enough, the system never gets a chance to evolve into a different state. You lock it in place by looking at it. Quantum tunneling pushes intuition even further. Particles can pass through energy barriers they shouldn't be able to cross. Imagine rolling a ball toward a hill. If the ball doesn't have enough energy to reach the top, it rolls back down. Classical physics says it can't get to the other side, but quantum mechanics says there's a probability it will appear on the other side of the hill anyway, as if it tunneled through. This isn't a metaphor. It's a real, measurable effect. Radioactive decay depends on it. The sun's fusion process depends on it. Scanning tunneling microscopes which image individual atoms depend on it. And the mechanism? There isn't one in the classical sense. The particle doesn't burrow through. It doesn't have a trajectory. It's simply more likely to be found on the other side than classical physics would allow. The wave function extends into the barrier, and there's a non-zero probability the particle will be detected beyond it. Measurement confirms this, but there's no story you can tell about how the particle got there. It didn't travel through space in the usual sense. It just transitioned. And some calculations suggest that the time it takes to tunnel through a barrier doesn't increase much as the barrier gets thicker, which raises the uncomfortable question of whether tunneling might allow information to propagate faster than light. Most physicists believe it doesn't violate causality, but there's no consensus on exactly why. As physicist Ephraim Steinberg put it, there's a mystery there, not a paradox. These aren't fringe ideas. They're mainstream physics, taught in universities, confirmed in laboratories, used in technology, but they refuse to resolve into a coherent picture. And what's most unsettling isn't that we lack the final answer. It's that after nearly a century of experimental success, the foundational questions still remain open. The math works, the predictions hold, but the meaning stays fractured. The question of what happens when you stop looking should be trivial. The coffee cup on your desk doesn't vanish when you turn your head. The moon doesn't flicker in and out of existence when no one observes it. Classical physics never asked whether objects needed permission to be real. They simply were. But quantum mechanics forces you to reconsider that assumption. And it does so not through philosophy, but through measurement. The most direct confrontation with this problem comes from wave function collapse. Before measurement, a quantum system exists in a superposition, a mathematical description that includes all possible outcomes simultaneously. The electron isn't here or there. It's described by a wave function that assigns probabilities to both locations. Then you measure, and the wave function collapses. The electron is found in one place, not both, not neither. One, but nothing in the Schrödinger equation, which governs how quantum systems evolve, predicts this collapse. The equation is deterministic, smooth, reversible. Collapse is sudden, discontinuous, irreversible. So where does it come from? The Copenhagen interpretation, formulated in the 1920s by Niels Bohr and Werner Heisenberg, treats collapse as a fundamental postulate. Measurement causes it, but the interpretation offers no mechanism. It doesn't explain what qualifies as a measurement. It doesn't specify when collapse occurs. It simply declares that upon observation, the system transitions from superposition to a definite state. And for practical purposes, this works. Physicists can calculate probabilities, design experiments, build technology. But the conceptual gap remains. Why does observation have this effect? What is special about measurement? And crucially, does the system have a definite state before measurement? Or does measurement create that state? The latter possibility is what makes this genuinely strange. It suggests reality at the quantum level is not observer independent. The electron doesn't have a position until you check. The photon doesn't have a polarization until you measure it. Properties emerge through interaction, not before. Einstein found this intolerable. In correspondence with Max Born, he wrote, "Do you really believe the moon isn't there when nobody looks?" For Einstein, the idea that observation creates reality was absurd. Physics should describe what is, not what we see. But the predictions of quantum mechanics, including wave function collapse, have been confirmed in every relevant experiment. So the question remains unresolved. Another approach attempts to avoid collapse entirely. The many worlds interpretation, proposed by Hugh Everett in 1957, takes the Schrödinger equation at face value. If the equation never includes collapse, then collapse never happens. Instead, when a measurement occurs, the universe splits. Both outcomes are realized, but in separate branches. You measure the electron's position. In one branch, you find it here. In another branch, you find it there. Both branches are equally real. Both versions of you exist, yet see, each experiencing a different result. From the perspective of any single observer, it looks like collapse, but globally, there's no collapse, only branching. This interpretation has the advantage of taking the mathematics seriously. It doesn't introduce an arbitrary collapse mechanism, but it introduces something else, an ontological extravagance. Every quantum event spawns new universes. The total number of branches increases exponentially. And there's no experimental way to access other branches, so the interpretation remains unfalsifiable. Some physicists embrace it, others find it unnecessarily baroque. The lack of consensus isn't due to insufficient data. It's due to the fact that all interpretations reproduce the same experimental predictions. They differ only in their metaphysical comportements, which raises an uncomfortable question. If multiple incompatible stories can account for the same observations, what does that say about the relationship between theory and reality? A third option, the de Broglie-Bohm interpretation, reintroduces determinism. It proposes that particles always have definite positions, guided by a pilot wave. The wave function doesn't collapse, it merely guides the particle's motion. Measurement reveals a pre-existing position, not one that emerges upon observation. This interpretation reproduces all quantum predictions while maintaining realism. Particles exist whether or not you look. But it introduces non-locality. The pilot wave is influenced instantaneously by distant measurements, and it requires hidden variables, quantities that exist but cannot be measured directly. Most physicists find this trade-off unappealing, so we're left with a fragmented landscape. Copenhagen says collapse happens, but doesn't explain it. Many Worlds says collapse doesn't happen, but multiplies universes. Bohm says collapse is unnecessary, but requires hidden machinery. And none of these interpretations can be ruled out experimentally. They're empirically equivalent. The question of what collapse is, or whether it even occurs, remains open. This isn't a gap waiting to be filled with more data. It's a conceptual problem embedded in the structure of the theory itself. And that brings us to the measurement problem's most troubling dimension, the role of the observer. If collapse occurs upon measurement, what counts as a measurement? Does it require a conscious observer, or is any physical interaction sufficient? If consciousness is required, then quantum mechanics has smuggled subjectivity into the foundations of physics. If consciousness isn't required, then the boundary between quantum and classical behaviour becomes arbitrary. John von Neumann, one of the architects of quantum theory's mathematical framework, took the former position seriously. He argued that the chain of measurement, detector, apparatus, environment, can all be described quantum mechanically. Each link can be placed in superposition. The only place the chain ends is with the conscious observer. Consciousness, in this view, is what collapses the wave function. Most physicists today reject this. It seems to grant consciousness an unwarranted role in physical law. But the alternative isn't much more comfortable. If consciousness doesn't matter, then at what point does a quantum system become classical? When does superposition give way to definiteness? The answer is supposed to be decoherence. When a quantum system interacts with its environment, it becomes entangled with countless degrees of freedom. The coherence that allows superposition to persist is lost. The system behaves classically, even though the underlying quantum description still applies. Decoherence happens fast. For most macroscopic objects, it occurs in fractions of a second, which is why you don't see everyday objects in superposition. But decoherence doesn't solve the measurement problem. It explains why superpositions become unobservable, but it doesn't explain why one outcome is realized rather than another. The wave function still includes all possibilities. Decoherence just makes them practically inaccessible. So collapse, or the appearance of collapse, still requires explanation. And the options remain the same. Either it's a real physical process we don't understand, or it's an artifact of how we describe the system, not a feature of the system itself. Eugene Wigner extended this problem into even stranger territory with a thought experiment. Suppose your friend is in a sealed lab, measuring the spin of an electron. From your friend's perspective, the measurement yields a definite result. Spin up, say, the wave function has collapsed. But from your perspective, outside the lab, the entire system, electron apparatus friend, is in superposition. Your friend is in a state of having measured spin up and a state of having measured spin down, both at once. So who's right? Your friend, for whom collapse has occurred, or you, for whom it hasn't? Wigner's friend's scenario reveals a deep tension. If collapse is objective, it should happen at the same time for everyone. But quantum mechanics allows different observers to disagree about when it happens. If collapse is subjective, then reality itself becomes observer-dependent, not in the sense that perception varies, but in the sense that what exists depends on who's looking. Recent variations on Wigner's scenario have formalized this tension. Daniela Frauchiger and Renato Renner showed that if you assume quantum mechanics applies to observers themselves, you can derive contradictory conclusions. Two observers, each applying quantum laws consistently, can arrive at incompatible statements about the same experiment. This doesn't mean quantum mechanics is wrong. It means something in the standard framework has to give. Either the theory doesn't apply to observers, or measurements don't have objective outcomes, or information about past measurements can't be freely used in future reasoning. Each option is uncomfortable, and none has achieved consensus. What makes this especially frustrating is that quantum mechanics works. The theory predicts experimental results with extraordinary precision. Technologies based on quantum principles, lasers, transistors, MRI machines, function exactly as expected. But the theory's success doesn't resolve its conceptual problems. You can calculate the probability that an electron will be detected at a particular location. You can verify that probability experimentally, but you can't explain why this particular electron, in this particular trial, was detected here rather than there. The math gives you probabilities, not stories. And when you ask what happens between preparation and measurement, when you ask what the electron is doing, the theory goes silent. Different interpretations fill that silence with different narratives, but the narratives aren't tested by experiment. They're chosen based on philosophical preference. Some physicists are comfortable with this, others find it unacceptable, and that division has persisted for nearly a century. Which brings us back to the original discomfort. The world around you appears definite. Objects have locations, events have outcomes, causes precede effects, but quantum mechanics, the theory that describes the microscopic substrate of everything, doesn't naturally produce that definiteness. It produces probabilities and superpositions. Definiteness emerges somewhere in the process of observation, but where and how and why, those questions remain unanswered. Not because we lack data, but because the data doesn't distinguish between fundamentally different metaphysical pictures. The problem isn't empirical, it's interpretive. And interpretation, unlike measurement, doesn't converge. This is the problem of interpretation, and it's not going away. Some physicists argue that interpretations don't matter. The theory works, it predicts, it calculates. Why worry about what's really happening? Paul Dirac once said, "Shut up and calculate." Except he never actually said that. The phrase is attributed to him, but it captures a real sentiment. Focus on the math, ignore the metaphysics, but that approach has limits. Because interpretations aren't just philosophical decoration. They shape how you think about new problems. They guide what experiments you design. They determine which questions seem worth asking. And when you're trying to extend quantum mechanics into new domains, quantum gravity, quantum cosmology, quantum information. The interpretive ambiguities become roadblocks. Take the many worlds interpretation. Hugh Everett proposed it in 1957. The idea is simple. There is no collapse. The wave function never reduces. When you measure an electron's spin, the universe splits. In one branch, you observe spin up. In another, you observe spin down. Both outcomes happen. Both versions of you exist. They just can't communicate. This solves the measurement problem cleanly. No special role for observers. No mysterious collapse mechanism. The Schrödinger equation holds everywhere, always. The cost? You have to accept that reality branches constantly, proliferating versions of yourself with every quantum event. Every time an electron interacts with a photon, the universe divides. Critics call this ontologically extravagant. Supporters call it mathematically elegant. Neither side can prove the other wrong. Because the theory makes the same predictions as standard quantum mechanics. The branches are mutually invisible. You can't detect the other worlds. You can only infer them from the math, or consider the pilot wave theory. Louis de Broglie proposed it in 1927. David Bohm revived it in 1952. The idea, particles always have definite positions. They're guided by a wave, the pilot wave, that obeys the Schrödinger equation. The wave isn't just a probability distribution. It's a real physical field that pushes particles along specific trajectories. This restores determinism. No randomness, no collapse. The electron really does go through one slit, but the pilot wave goes through both. The wave interferes with itself, guiding the particle to create the interference pattern. The appearance of randomness arises because we don't know the particle's initial position with infinite precision. But in principle, the motion is deterministic. The catch, the theory, is non-local. The pilot wave for one particle depends instantaneously on the positions of all other particles. Change something here, and the wave adjusts there, faster than light. That doesn't allow faster than light signaling, but it does mean the universe is deeply interconnected in a way that violates the spirit of relativity, even if it doesn't violate the letter. Then there's the Copenhagen interpretation, or rather, the family of interpretations called Copenhagen. Bohr, Heisenberg, Born, they didn't all agree on the details, but the core idea, quantum mechanics describes what we can know, not what is. The wave function represents our information about a system. Measurement updates that information. Collapse isn't a physical process, it's an epistemic one, a change in knowledge, not in the world. This avoids ontological commitments. You don't have to say what the electron is doing before measurement. You just say what the theory predicts about measurement outcomes. It's pragmatic, it's operationalist, and it drives realists crazy. Because it sidesteps the question of what's actually happening. Each interpretation solves some problems while creating others. Many worlds eliminates collapse but multiplies realities. Pilot wave restores determinism but sacrifices locality. Copenhagen avoids ontology but leaves causation unclear. And there are others. Objective collapse theories, modal interpretations, consistent histories, each with its own trade-offs. What's frustrating is that you can't decide between them experimentally. They make identical predictions for any measurement you can perform. The differences lie in what they say about the unmeasured, the unobservable, the in-between. And science traditionally doesn't adjudicate metaphysics. It tests predictions. When predictions align, the metaphysics remains open. Still, the interpretive divide matters, because it reveals something uncomfortable. Quantum mechanics is extraordinarily successful, but we don't agree on what it means. We don't agree on what exists. We don't agree on how causation works. We don't agree on the role of time. And we've lived with this disagreement for decades. That's not normal. In classical physics, there was general consensus about what the equations described. Maxwell's equations describe electromagnetic fields. Newton's laws describe forces and motion. Einstein's equations describe space-time curvature. You could argue about deeper issues. What is a field really? What is space? But there was rough agreement about what the theory was talking about. Quantum mechanics doesn't have that. It has a mathematical formalism that works flawlessly. But when you ask what the formalism refers to, you get fundamentally different answers. And those answers aren't converging, they're multiplying. One reason interpretations persist is that each captures something intuitive. Many worlds respects the universality of quantum mechanics. Why should macroscopic systems obey different rules than microscopic ones? If the Schrödinger equation governs atoms, why not brains? Pilot wave respects the intuition that particles exist and move. Objects have trajectories. They occupy space. That's basic. Copenhagen respects the pragmatic success of quantum mechanics. The theory works. Don't overcomplicate it. But intuitions conflict. And physics doesn't have a procedure for resolving intuitive conflicts when the empirical evidence is identical. You can't run an experiment to determine which intuition is correct. You can only clarify what each intuition commits you to and see which commitments you're willing to accept. Some physicists hope that future experiments will distinguish interpretations. Perhaps tests involving quantum gravity or cosmology will reveal new effects that break the symmetry. Perhaps advances in quantum computing will expose interpretive differences. But so far, the evidence points the other way. The more precisely we test quantum mechanics, the more it conforms to the standard predictions. The interpretive ambiguity remains. Others argue that the problem isn't empirical but conceptual. The interpretations aren't rival theories. They're different ways of organising the same facts. Like describing a landscape from different angles, the landscape doesn't change. Only the description does. If that's true, then searching for the right interpretation is misguided. There isn't a right one. There are only different frameworks, each useful in different contexts. But that view has its own discomfort, because it suggests that reality doesn't have a structure independent of our descriptions, that what you see depends on how you look, not in the trivial sense that perspective matters, but in the deeper sense that there's no fact of the matter about what's happening between measurements. The electron doesn't have a trajectory, it doesn't have a position, it doesn't have properties until you measure it, and even then, the properties you find depend on what you measure. This is where the interpretive problem becomes a metaphysical problem, and metaphysics traditionally isn't physics, it's philosophy, but the boundary is blurry. Because the questions quantum mechanics raises aren't idle speculation, they're forced by the theory itself. The formalism doesn't tell you what exists, it tells you what to expect. And when you try to connect expectation to existence, you run into walls. The walls don't mean quantum mechanics is wrong. They mean it's incomplete in a specific sense. Not that it's missing equations, but that it's missing an account of what the equations describe. And without that account, you're left calculating without understanding, predicting without explaining. Which works practically, but leaves something unresolved. You might ask, does it matter? If the predictions are correct, why care about the interpretation? Because science isn't just prediction, it's also explanation. An explanation requires saying what's going on, not just what will happen, but why and how. and what that means for the structure of reality. Quantum mechanics gives you the what will happen, but the why and how remain contested. And that's the situation. A theory of extraordinary precision, of universal applicability, of technological indispensability, but one whose meaning remains elusive, one whose ontology remains undecided, one whose interpreters cannot agree on what they're interpreting, not because the evidence is unclear, but because the evidence underdetermines the conclusion. Multiple stories fit the data equally well, and there's no experiment that picks the winner. So the landscape you're left with is one where the mathematics works impeccably, where every experiment confirms what the equations predict, where technological applications multiply daily, but where the conceptual ground remains unstable. And that instability isn't going to be resolved by better instruments. It's not a measurement problem, it's an interpretation problem. And interpretation problems don't yield to data alone. They require something else. A framework, a metaphysics, an account of what exists when no one is looking. Which brings us back to observation, because however you interpret quantum mechanics, observation plays a role that's deeply uncomfortable. Not observation in the casual sense of seeing something, but observation in the technical sense of interaction, of entanglement, of information transfer. The moment a quantum system interacts with something large enough to be classical, something changes. The wave function collapses. The superposition resolves. The many become one. And that transition from indefinite to definite is where all the trouble lives. In the Copenhagen interpretation, measurement causes collapse. The act of observing forces nature to choose. Before measurement, the electron is everywhere. After measurement, it's somewhere. And the mathematics of quantum mechanics tells you the probabilities, but it doesn't tell you why this electron ended up here rather than there. It doesn't explain the mechanism of collapse. It just says that's how it works. Measurement selects, reality crystallizes. Don't ask why, it's a postulate. But that postulate sits awkwardly with the rest of physics, because everywhere else, physical processes are continuous, deterministic or probabilistic, but governed by equations. Collapse isn't governed by an equation. It's an additional rule, a discontinuity, and discontinuities demand explanation. You can't just say this is what happens, you have to say why. And Copenhagen doesn't. It defers, it says measurement is primitive. It says consciousness or macroscopic apparatus or environment triggers collapse. But it doesn't specify which. It doesn't give you a criterion. It leaves the boundary vague. Many worlds removes collapse entirely. It says the wave function never collapses. It just evolves. The universe splits. Every possible outcome happens. You see spin up. Another you in another branch sees spin down. Both outcomes are real. Both branches exist. And the mathematics supports this. Because the Schrödinger equation is linear. It doesn't include a collapse term. So if you take the equation seriously, without adding postulates, you get branching. You get multiplicity. You get a universe that's constantly dividing into parallel realities. But that comes with its own discomfort, because you never experience the split. You only experience one outcome, one branch, and the other branches are inaccessible, undetectable. They exist in the mathematics, but not in your experience, which makes them unfalsifiable. And unfalsifiable claims sit poorly in science, not because they're wrong, but because they can't be tested. You can't prove the other branches exist. You can only say the mathematics implies them, and that's a weaker kind of evidence. Pilot wave theory restores determinism. It says particles have positions, always. They follow definite trajectories, guided by a wave. The wave evolves according to Schrödinger's equation. The particle follows the wave, and together they reproduce all the quantum predictions, interference, entanglement, everything. But the particle is always somewhere. The wave is always real. An observation doesn't collapse anything. It just reveals where the particle was all along. This feels more intuitive, more classical, but it has its own costs. The wave is non-local. It extends across space, and changes to the wave anywhere affect the particle instantly. No matter the distance, which means faster than light influence, not of information. You can't use it to send signals, but of dynamics. The particle's motion here depends on the wave's configuration there, instantly, non-locally, and that's hard to reconcile with relativity, which says nothing travels faster than light, including influences. Pilot wave theorists argue that the non-locality is hidden, that it doesn't allow signaling, that it's compatible with relativity in a technical sense, but it remains conceptually uncomfortable. Because relativity isn't just about speed limits, it's about locality, about the idea that distant events don't directly affect you, and pilot wave theory violates that, subtly, unavoidably. Each interpretation, then, solves some problems and creates others. Copenhagen preserves locality, but introduces collapse. Many worlds preserves determinism, but multiplies realities. Pilot wave preserves realism, but embraces non-locality. And there are others. Objective collapse theories, quantum Bayesianism, consistent histories, each with its own trade-offs, each with its own conceptual costs. And none of them changes the predictions. They all agree on what you'll measure. They only disagree on what's happening when you're not measuring, which makes the disagreement metaphysical rather than empirical. And metaphysics, historically, hasn't been physics. But in quantum mechanics, the line blurs, because the theory forces you to make metaphysical choices. It doesn't let you avoid them. You have to decide what exists, what's real, what counts as an observer. And those aren't scientific questions in the usual sense. They're interpretive questions, philosophical questions, questions about the relationship between mathematics and reality, which is why the interpretive debates persist, not because physicists are stubborn, but because the theory itself is silent on these issues. It gives you probabilities. It doesn't give you ontology. And when you try to extract ontology from the mathematics, you find that multiple ontologies fit equally well, like different maps of the same terrain, each accurate, each useful, but none uniquely correct. And that's the situation, a theory that predicts with extraordinary precision, that describes phenomena from atoms to cosmology, that underlies all of modern technology, but one whose meaning remains contested, whose ontology remains ambiguous, whose fundamental nature remains unclear. Not because the experiments are inconclusive, but because the experiments confirm the mathematics without resolving the interpretation. The data is consistent with multiple stories, and there's no experiment that picks the winner. So you're left calculating, predicting, building quantum computers, designing experiments, but without a settled account of what you're computing or predicting or building, without agreement on what exists when no one is looking, without consensus on what observation does. And that's not a failure of the theory, it's a feature or a consequence of a theory that describes nature at a level where our classical concepts break down, where the distinction between wave and particle dissolves, where the boundary between system and observer blurs, where reality itself seems to depend on context. And perhaps that's the real lesson. Not that quantum mechanics is weird, but that reality is weirder than we thought. That our intuitions, honed by macroscopic experience, don't extend down to the quantum scale. that nature doesn't owe us comprehensibility, it only owes us consistency, and consistency it delivers. The mathematics works, the predictions hold, the technology functions. What's missing isn't correctness, it's comfort. The feeling that we understand what's going on beneath the equations. And maybe that feeling was always an illusion, a projection of human psychology onto a universe that doesn't share our categories. The quantum world doesn't split neatly into objects and properties, into things and states, into what exists and what we know. It blurs those distinctions. It forces you to recognize that knowledge and existence aren't separate, that observation isn't passive, that measurement isn't neutral, and that makes it uncomfortable because we built our entire conceptual framework on the assumption that the world exists independently of us, that we can study it from outside, that we can describe it objectively. And quantum mechanics suggests that assumption fails, at least at the quantum level, and maybe beyond, which leaves you in a strange position, using a theory that works perfectly. That's never been contradicted by experiment, but that refuses to give you a picture of reality you can hold on to. That refuses to answer the question, what's really happening? And maybe that's the point. Maybe the question is malformed. Maybe reality doesn't have a structure that exists independently of how you probe it. Maybe what you find depends on what you ask, not arbitrarily, but fundamentally. And that's the most unsettling implication of all, because it suggests that the universe isn't a fixed stage with actors playing roles. It's a process, a dialogue, an interaction between systems and observers. And the boundary between those two is itself context-dependent. So the paradoxes don't resolve. They coexist, and you learn to live with them, to work with them, to accept that understanding isn't always available, that sometimes all you get is calculation and prediction and technology, but not meaning. Not in the sense you want, not in the sense that lets you say, this is what's really going on. Because quantum mechanics doesn't give you that. It gives you something else. A map that works, a formalism that predicts, a structure that succeeds, but a structure whose relationship to reality remains, after nearly a century, genuinely unclear. And that ambiguity isn't going away. It's part of the package, part of what it means to describe nature at the quantum level, where the questions you ask shape the answers you get, where observation isn't neutral, and where the deepest truths remain stubbornly and perhaps permanently interpretive rather than empirical. But then something else happens, something that pulls you further from stability. You discover that quantum systems don't just refuse to behave like classical objects, they refuse to behave consistently with themselves. Take the quantum Zeno effect, named after the ancient Greek philosopher who argued that motion is impossible because an arrow never moves during any single instant. The quantum version takes that logic and makes it real. If you measure a quantum system repeatedly, constantly checking its state, you can prevent it from evolving. You freeze it in place, not by interfering mechanically, just by looking. An unstable atom should decay. That's what unstable means. But if you check whether it's decayed often enough, it won't. The measurement itself locks the system into its initial state. The more you observe, the less it changes. This isn't speculation. It's been demonstrated in trapped ions, in superconducting circuits, in commercial magnetometers. It's even suspected to play a role in how birds sense magnetic fields. The effect is real, the mechanism is clear, and it makes no intuitive sense whatsoever, because classically, observation is passive. You look at something to find out what it's doing. You don't expect the act of looking to alter the fundamental dynamics. But quantum mechanically, observation isn't passive. It's an interaction. And interactions have consequences. In this case, the consequence is that the system can't leave its initial state because you keep resetting it with each measurement. It's like checking if water is boiling by constantly opening the lid. Except instead of just slowing the process, you stop it entirely. The system becomes trapped in a loop where it never has time to evolve between observations. And that raises a question that's harder than it sounds. What counts as an observation? Does it require consciousness, a detector, any interaction with the environment? And how frequent does it need to be to freeze the evolution? The mathematics gives you precise answers, but those answers depend on parameters that feel arbitrary. The rate of measurement, the strength of coupling to the environment, the definition of what constitutes a distinct measurement event. And none of that maps cleanly onto the idea of observation as something a person does, which means the effect is telling you something about the structure of quantum mechanics itself. Not about minds or awareness, about the relationship between systems and the act of probing them. Now consider tunneling, another phenomenon that refuses classical logic. A particle encounters an energy barrier, a wall it doesn't have enough energy to climb over. Classically, it bounces back. Quantum mechanically, it has a probability of appearing on the other side. It tunnels through. This isn't metaphorical. It's the mechanism behind radioactive decay, nuclear fusion in stars, and the operation of tunnel diodes. It's why the sun shines. It's why alpha particles escape atomic nuclei. It's not exotic, it's fundamental. But here's where it gets strange. Not just that tunneling happens, but the time it takes. In 1962, physicist Thomas Hartmann calculated something odd. The time a particle spends tunneling through a barrier doesn't increase much with the thickness of the barrier. Make the barrier thicker, and the tunneling time barely changes. Thick enough, and particles could appear to cross faster than light would travel the same distance through empty space. That sounds like a violation of relativity, but it's not, because you can't use tunneling to send information faster than light. The effect is statistical. You can't control which particle tunnels when, and the group velocity of the wave packet isn't the same as signal velocity. But still, the math suggests that during tunneling, something happens that doesn't fit the usual picture of particles moving through space at subliminal speeds. It's not that particles travel faster than light, it's that the concept of travel during tunneling becomes poorly defined. Because tunneling isn't motion in the classical sense, it's the quantum amplitude leaking through a forbidden region. The particle doesn't have a trajectory through the barrier. It exists as a probability distribution that extends into classically forbidden territory. And when you measure where it is, you find it on the other side, without it ever having been inside the barrier in a way you could have detected. This creates what physicists politely call a mystery rather than a paradox, because while it doesn't violate any known law, it defies the intuition that motion should be continuous, that particles should have paths, that if something gets from here to there, it must have been in between. Tunneling says, not necessarily. Then there's decoherence, the process that explains why you don't see quantum superpositions in everyday life, why chairs don't exist in two places at once, why cats are either alive or dead, not both. Decoherence is the loss of quantum coherence. It happens when a quantum system interacts with its environment. The system becomes entangled with countless environmental degrees of freedom. And that entanglement causes the distinctive quantum properties, superposition and interference, to vanish. But notice the wording, vanish, not disappear. The coherence isn't destroyed, it's diluted. spread out over so many environmental states that it becomes effectively unobservable. It's like dropping ink into the ocean. The ink doesn't cease to exist, but you'll never collect it again. The information is still there, in principle, but it's irretrievably scrambled into the environment. This process is incredibly fast for macroscopic objects. A dust particle decoheres in less than a billionth of a second. Anything larger, even faster. Which is why you never see quantum superpositions of everyday things. They decohere before you could possibly measure them. And this solves, or seems to solve, the measurement problem. Because if decoherence happens automatically whenever a quantum system interacts with a macroscopic environment, then measurement isn't special. It's just decoherence caused by interaction with the detector, except it doesn't solve the measurement problem. Not really, because decoherence explains why you see definite outcomes. It doesn't explain which outcome you see. After decoherence, the system and environment are in an entangled state, where different outcomes correspond to different environmental states. But the wave function still contains all possibilities. The superposition hasn't collapsed, it's just been hidden by entanglement. So decoherence explains the appearance of collapse, but it doesn't explain collapse itself. It shifts the problem from the system to the environment. But the environment is quantum too, so the same question remains. When does the wave function actually collapse? Or does it collapse at all? This is where interpretations diverge. Copenhagen says collapse happens at measurement, but doesn't specify when or how. Many worlds says collapse never happens, and all outcomes exist in parallel branches. De Broglie-Bohm says particles have definite positions all along, guided by a pilot wave. Objective collapse theories say collapse is a real physical process triggered by gravity or some other mechanism. Each interpretation handles decoherence differently. But none of them are forced by the mathematics. They're all consistent with the same experimental predictions, which means the choice between them isn't empirical, it's philosophical. And that's the uncomfortable part. Not that we don't know which interpretation is correct, but that the question might not have an empirical answer, that the mathematics works regardless of how you interpret it, that the formalism is more fundamental than the picture. Now add wave function collapse itself. The thing decoherence was supposed to explain but doesn't quite. In the Copenhagen interpretation, collapse is a postulate. It happens when you measure. The wave function, which was evolving smoothly according to the Schrödinger equation, suddenly jumps to a definite state, and future evolution proceeds from that state. But there's no equation for collapse, no mechanism, no specification of when it occurs. It's not part of the dynamics. It's an extra rule you add to make the theory match observation. And that asymmetry between smooth evolution and abrupt collapse has bothered physicists since the beginning, because it suggests the theory is incomplete, that there's something going on during measurement that the formalism doesn't capture. Some interpretations try to fix this. Objective collapse theories add new terms to the Schrödinger equation that cause spontaneous collapse. Many worlds removes collapse entirely by saying it never happens. De Broglie-Bohm avoids it by giving particles definite positions, but each solution introduces new complications. Objective collapse requires specifying when and why collapse occurs, and no proposal has been experimentally confirmed. Many worlds requires accepting an enormous ontology of parallel branches. De Broglie-Bohm requires a non-local guiding wave, so you're left with a choice: either accept collapse as a brute fact, or replace it with something else that brings its own difficulties. And neither option feels satisfying, because what you want is a theory that's both complete and minimal. That explains everything without adding unnecessary structure. And quantum mechanics, for all its success, doesn't give you that. It gives you a formalism that works but leaves interpretive freedom about what's really happening. And maybe that's the pattern. Not that quantum mechanics is broken, but that it's doing something different from what physics used to do. It's not giving you a picture of reality. It's giving you a set of rules for calculating probabilities. And those rules don't require, or perhaps don't permit, a single underlying picture. Which means the paradoxes aren't failures. They're symptoms, signs that you're asking for something the theory isn't designed to provide. Asking what's really happening, when the theory only tells you what you'll observe. And that gap between what happens and what you observe is where all the discomfort lives, because it forces you to confront the possibility that observation isn't just how you learn about reality. It's part of how reality is structured, at least at the quantum level. And if that's true, then the universe doesn't exist as a set of definite facts waiting to be discovered. It exists as a set of potentials waiting to be actualized through interaction. And you, the observer, are part of that interaction, not passively recording, but actively participating in the process that brings facts into being, which is either profound or deeply unsettling, depending on how you hold it. And maybe that's the real pattern you're staring at. Not that reality is unknowable, but that knowability depends on the frame you're using to ask, which means different frames give you different answers, and no single frame captures everything. And if you accept it, then the paradoxes aren't bugs. They're diagnostic tools. They show you where your frame is breaking down, where the concepts you're using to structure the question no longer map cleanly onto what's happening. Take quantum tunneling. Particles passing through barriers they don't have the energy to cross. Classically impossible. But quantum mechanically, it's just what probability distributions do. The wave function extends into the barrier. Most of the time it doesn't make it through, but occasionally it does. And when you measure, you find the particle on the other side. No violation, no paradox, just a mismatch between classical intuition, which treats particles as localized objects, and quantum reality, which treats them as probability amplitudes. The paradox dissolves when you stop asking how the particle got through, because that question assumes it followed a path. And paths are classical concepts, so you're importing classical structure into a quantum situation and then being surprised when things don't fit. But if you just calculate the amplitude for being on the other side, the math works perfectly. No mystery, except that it still feels like a mystery, because your brain evolved to track objects moving through space, not probability clouds leaking through barriers. And that disconnect between how it feels and what the math says is where the discomfort lives. Now add the quantum Zeno effect. If you measure a system constantly, it stops evolving. You can freeze it in place just by looking at it too often, which sounds absurd, like watching a pot prevents it from boiling. But it's real. And it's been demonstrated in labs. The mechanism is straightforward. Each measurement collapses the wave function. And if you collapse it before it has time to evolve significantly, it keeps resetting to the same state. So continuous measurement prevents transitions. It's not that observation has magical power. It's that measurement is an interaction, and interactions have consequences. The system couples to the measuring device, decoheres, and gets projected onto a definite state. Do that fast enough. GH, and the system never leaves that state. But here's where it gets uncomfortable. Because this isn't some exotic laboratory trick. It's happening all the time. Every time your environment interacts with a quantum system, it's performing a measurement, which means the universe is constantly Zenoing itself, preventing transitions by virtue of being entangled with everything around it. And that's why macroscopic objects don't behave quantum mechanically, not because they're too big, but because they're too coupled, too entangled with their surroundings to maintain coherence. Which brings you back to decoherence and the question of why macroscopic superpositions don't exist. Not because collapse is real, but because the environment is constantly measuring. And that measuring, that entangle, destroys interference before you can observe it, except that doesn't fully solve the problem. Because decoherence explains why you don't see superpositions, but it doesn't explain why you see one outcome instead of another. It tells you the off-diagonal terms in the density matrix go to zero, but it doesn't tell you which diagonal term you'll end up in. That's still left to collapse, or to interpretation. So decoherence pushes the problem back, but it doesn't eliminate it. You still need something to select the outcome, which is why different interpretations handle it differently. Copenhagen says collapse is fundamental. Many worlds says all outcomes occur. De Broglie-Bohm says particles have definite positions, and each interpretation has its own way of dealing with measurement. But none feels complete, because each one either adds structure that seems arbitrary, or removes structure that seems necessary. Copenhagen adds collapse without explaining it. Many worlds adds infinite branches without explaining why you experience one. De Broglie-Bohm adds a guiding wave that's undetectable, so you're trading one discomfort for another. And that's the situation physics is in. Not stuck, but faced with a choice that doesn't have a clear winner. Because the formalism works, the predictions match experiment, but the interpretation remains open. And maybe that's not a failure. Maybe it's a sign that the theory is doing something different, not describing reality, but constraining experience, giving you rules for what you'll observe without committing to what exists independently. Which is a strange kind of science, because science used to be about discovering what's there, finding the structure underneath the phenomena. But quantum mechanics might be telling you that what's there depends on how you look, that the structure isn't independent of observation. And if that's true, then the paradoxes aren't failures of understanding. They're signals that you're asking the wrong kind of question, asking what's real, when the theory only tells you what's observable. And the gap between those two, between real and observable, is where all the discomfort lives. Because it forces you to consider that maybe there isn't a deeper reality, or if there is, it's not accessible in the way you thought. That the universe doesn't exist as a set of facts waiting to be discovered. It exists as a set of correlations waiting to be actualized through interaction. And you're part of that interaction, not outside it, not observing from a distance, but embedded in the process, shaping outcomes through the very act of measuring. Which doesn't mean you create reality, but it does mean you participate in it, in a way that's deeper than classical physics allowed. And that's unsettling, because it removes the safety of objectivity, the idea that the world is what it is, regardless of you, and replaces it with something more entangled, where what you find depends on what you ask, and what you ask depends on the apparatus you use, and the apparatus depends on the theory you're testing. So there's no view from nowhere, no God's eye perspective, just different frames, different ways of carving up experience, and each one reveals something, but none reveals everything. Which brings you to a final question, not whether quantum mechanics is true. It is. The predictions work, but whether it's complete, whether there's something underneath it, some deeper layer that would make the paradoxes go away. And the answer so far is no. Every attempt to add hidden variables runs into Bell's theorem. Every attempt to restore locality runs into experimental violations of Bell inequalities. Every attempt to make measurement classical runs into the quantum Zeno effect, or decoherence. So if there's a deeper layer, it's not accessible through classical concepts, which means either the theory is complete and reality is just strange, or the theory is incomplete and we don't yet know what as missing, and physics doesn't have a way to decide between those options, because both are consistent with everything we've observed. So the paradoxes remain, not as failures, but as reminders that the universe doesn't owe you intuition, that the math works even when the pictures don't, and that maybe, after a century of trying, the discomfort is the point, the signal that you've reached the edge of what classical thinking can handle, and what lies beyond isn't chaos, it's just a different kind of structure, one that requires letting go of the idea that observation is separate from what's observed. That maybe the deepest lesson of quantum mechanics isn't about particles or waves or measurement, it's about the limits of separation itself. The idea that there's a world out there, independent of you, waiting to be discovered. Quantum mechanics suggests that picture is too simple, that reality is relational, defined by interactions, and you're part of those interactions, not as an observer standing outside, but as a participant embedded within. And that's not mysticism, it's mathematics. It's what the formalism has been saying all along. If you're willing to listen, and maybe that's where you are now, sitting with the realization that quantum mechanics doesn't give you closure, it gives you precision without comprehension, predictions without pictures, a formalism that works flawlessly but refuses to resolve into something you can visualize or hold steady in your mind. The paradoxes aren't going away. Schrödinger's cat still sits in its box, neither alive nor dead until you open it. The double-slit experiment still produces interference patterns that vanish the moment you try to see which path the particle took. Bell's inequalities are still being violated in laboratories around the world, confirming that either locality or realism has to give. The quantum Zeno effect still freezes systems in place through observation alone. Tunneling still allows particles to appear where they shouldn't be, in times that don't quite add up. And decoherence still explains why you don't see macroscopic superpositions, but not why you see the particular outcome you do. Each paradox points to the same underlying tension, the gap between what the mathematics describes and what your intuition expects, between what the formalism predicts and what a coherent picture of reality would look like, between the rules for calculating probabilities and an account of what's actually happening. And after a century of experimental confirmation, of technological application, of theoretical refinement, that gap hasn't closed, it's widened. Because the more precisely we test quantum mechanics, the more it confirms predictions that strain classical understanding. The more we try to visualize what's happening, the more we find that visualization itself might be the problem. Not because nature is trying to hide from you, but because the concepts you're using, particle, wave, trajectory, position, observation, are approximations, tools that work at certain scales but break down when you push them too far. And quantum mechanics is where they break, where the clean separation between observer and observed, between what exists and what you know, stops making sense. So maybe the lesson isn't that quantum mechanics is incomplete. Maybe it's that completeness looks different from what you expected, that a complete theory doesn't have to give you a picture. It just has to give you rules that work. And if those rules produce paradoxes when you try to force them into classical frameworks, that's not a failure of the rules, it's a failure of the frameworks. The universe isn't obligated to make intuitive sense. It's only obligated to be consistent with itself. And quantum mechanics is consistent, internally coherent, empirically verified. The paradoxes aren't contradictions. They're signals that your intuitions, your mental models, your inherited assumptions about how reality should work, those are what need updating. But that updating is hard, because it's not just about learning new facts. It's about letting go of old certainties, about accepting that observation isn't neutral, that reality might be contextual, that the boundary between what exists and what's measured might not be as clear as you thought, about living with interpretive freedom instead of interpretive closure. And that's uncomfortable, not because the science is unclear, but because the implications resist containment. They keep spilling over into questions about what it means to know something, to observe something, to exist as something that observes. Questions that physics alone can't answer because they're not purely physical. They're conceptual, philosophical, about the relationship between mathematics and meaning. The paradoxes refuse to make sense, not because they're wrong, but because sense-making itself is a frame. And quantum mechanics operates at a level where that frame starts to wobble, where the distinction between map and territory, between description and reality, becomes less stable than you need it to be. And maybe that instability isn't something to fix. Maybe it's something to recognize, to sit with, to understand as a feature of how knowledge works at the boundary of what can be known. You wanted certainty, you got calculation, you wanted pictures, you got probabilities, you wanted to understand what's really happening. And what you found is that really might be the wrong question, because it assumes there's a fact of the matter independent of how you look. And quantum mechanics suggests that assumption doesn't hold, at least not cleanly, at least not all the way down. So the paradoxes remain, not as puzzles waiting to be solved, but as landmarks, indicators that you've reached the edge of classical thinking, that the tools you brought from everyday experience don't extend this far. And what lies beyond isn't chaos or confusion, it's just structure of a different kind. One that doesn't separate observer from observed. One that doesn't privilege existence over interaction. One that treats reality not as a collection of facts, but as a web of correlations that crystallize through measurement. And perhaps the most unsettling part isn't that quantum mechanics refuses to give you a clear picture of what's happening. It's that the refusal itself might be the answer. That the theory is telling you something fundamental about the limits of representation, about how far you can push the idea of an objective, observer-independent reality before it stops being useful. Before the questions you're asking stop having definite answers, not because the universe is hiding anything, but because the structure of the universe doesn't support the kind of definiteness you're looking for. And learning to work with that rather than against it might be what understanding actually requires.